Thank you very much. So it's going to be a kind of introduction, simple or not too many detail. So what is that? So maybe you know what is ω-categorical, you know what is a Banach space, and what are these orbit spaces. If you know what ω-categorical is, maybe you get what it is, but if not, I will explain you. Well, this is a joint work with part of a joint work with Valentin Ferenczi and Victor almost Prieto, which is the final part of his PhD. So this is more or less what I'm going to do, introduction, and there will be two kind of spaces which are very simple, more or less, and you might understand what they are, which are C of K spaces for very particular K, and X. X is going to be a either metric space or in general, which is, or in particular, I would say, Banach space. Wagner spaces, which is the similar, but now with the LP. Instead of continuous mappings, integral, integrable. And in this case, in this last part, I will talk about these spaces, L4, L6, L8, and so, which are very particular ones. Okay, so this is a very general question, which is the first question we had in order to then develop what we did afterwards, which is this kind of esoteric, one might say, but then once you are there, it's not so esoteric. So imagine that there is a way to determine shape determines the placement of this shape of this thing inside another big thing, right? So I'm thinking, of course, is going to be a Banach space or metric space. And imagine that I know that some submetric space or subspace is isometric to another subspace. Is this the case exactly when I can move the first one to the second one by an isometry? So the way they are, the ball, which is how they look like, if it is spherical, determines the place they will have inside a bigger space, right? So, and in certain cases, this is the case, and certain other cases, so in the most of the cases, this is not the case, but in certain cases, very close to cases where it is the case, it is not. So we want to understand why that, right? I don't know if I am being too esoteric.
So
It will be less esoteric in a moment, right? Yes?
Is it just obvious if we're in Rn or something like this? I mean, subspaces are like planes or something.
But when I say the position, you have to tell me what does this mean? You see, this is the equivalent class determined by being moved by an isometry. And then you need to determine what is an isometry.
Yeah, sure.
You see, these are all these things that they will come.
Okay.
Well, this is what I said. It's exactly there, right?
And is it also obvious that you, or example, that you can't send X to Y via global isometry? That must be easy.
Exactly. Then they have the same shape. So the other way around is true. If you can move it same place, of course, they must be isometric. They must look the same, right?
But what is direction? Is there an easy counterexample that?
Many of them, most of them are not. So I will tell you what is that. This is what is called ultra homogeneity or approximate ultra homogeneity. And as we know, especially here, it is very particular to be approximate ultra homogeneous or ultra homogeneous, right? But of course, all this started with discrete structures, first order structures. Now you can talk about them exactly in these other metric structures, right? In particular in Banach spaces. Well, and then once you know that if the placement and the shape are the same, essentially you would like to know if they are topologically the same. Yes? Okay, and now it comes this thing about the ultra homogeneity that you have a countable structure. And one says that this countable structure is ultra homogeneous if every isomorphism between substructures which are finite or finitely generated, maybe in some cases you can also say this way, is the restriction of a global surjective isometry automorphism. Excuse me, I am going to confuse because I have always in mind isometries, but of course, here in this context is an automorphism, yes? And then there are these two correspondences, the Fraise correspondence and the KPT correspondence, Kekris, Pestov, and Todorchevich. The first one is telling you that the limit, there is this structure which is ultra homogeneous, and this is exactly a property of the H. And as you know, is this amalgamation property. These other two are very simple. Hereditarily property and joint embedding, these are very simple, but the key one is this amalgamation, which is a local version kind of ultra homogeneity. Yes? And then the second one is not just talking about the relation between a property of the H and the structure M limit, but the automorphic group of M. And it is a strengthening of the amalgamation, which is the Ramsey property. Ramsey property plus joint embedding implies directly amalgamation. It's rather easy. You play, well, this is easy. And now the output is that you know that the automorphic group is extremely amenable. Yes? We are not going to go through this, but there is the similar scenario for metric structure, in particular for Banach spaces, and you have exactly the same two things. Yeah? Well, continuous logic. The interest for me is that now you can talk about so many things in model theory, but now for Banach spaces, for example, in the same way. Simply that now you need to re-understand what a relation is, what a mapping, what an operation is, etc., etc. Yes? I'm not going to talk about this. Okay, and now approximate ultra homogeneity. What is that? Well, metric. There is a metric now, and this is very important because now there is an error. There is an epsilon. You can say you are close to B, whatever. And this is what it is, because in this discrete thing, in this continuous thing, being equal up to epsilon is the same that being equal. So having this in mind, what does this mean to be approximately ultra homogeneous? That whenever you have an embedding from a finite dimensional space, so what I'm using here, and this is finite dimensional, and you have a gamma. So there are many ways to say this, right? This linear, now everything will be this way, and isometry. And for every epsilon, there is an isometry, surjective, linear isometry, such that I would like to say this thing. Hey, hi. But this is not true, and this is very, very strong, and this, hi. And this will become, this is an open problem if there is only one example we know, which is the Hilbert spaces, and it's a big, big, big open problem on that if this is the only one. But there are other examples which exist and they are not Hilbert, where you have this. And what is that? This is the typical thing, right? You think this as a continuous mapping in the unit balls, so in the unit ball of X, so this is the supremum or maximum in the ball of X. There are many ways to say. Yes, this is compact, and this makes sense, right? This is a standard thing. This is the operator. Operator now. I'm being a little precise for these things, maybe if you are not used to.
I'm sorry, I didn't hear what you said, but you said there's some big open problem. What was
Yes,
it?
if so, this is true.
Oh, for equality, I
If
see, okay, gotcha.
yes, so there is this thing I told you distinguishing
Fine, okay.
being equal or being almost
So
equal
the only example. no,
is the Hilbert space. Yes,
What is almost isometry? Sorry, I missed.
a global. This is false. This is not as it should be.
Oh,
This is not well written. Instead to a global is no to a no. This is don't pay attention to that. This is what I said.
sorry.
So this
Projective and E is finite dimensional. Okay.
no. E is the big guy.
X is fine.
X is finite
At
dimensional.
BC, you have this.
So you have
X.
and gamma is just linear. It's not isometry or anything. Oh,
Gamma is an
it
isometry.
yes.
So you
for
have
every
that.
epsilon. For every epsilon you have
Yes,
approximate.
this please don't pay attention to that because exactly that is a big distinction between this, which is not correct, and that. Yes,
I see. And you're okay. So for
because it's not true that an epsilon isometry, which you might guess what it is, you can change this by these kind of things, right? It is not true that every perturbation, everything close to an exact isometry is an epsilon isometry. It's an almost isometry. But it's not true in general that every almost isometry is close to an isometry. This is not true. This is false. Okay, so don't pay attention to that. I will erase that. I'm very sorry, no, because I really okay.
But can I just ask?
Yes.
So if you insist on isometry on the nose, then this is Hilbert space, right?
For the moment, yes, but nobody knows if this is the only. If this is a characterization.
The nose, it's possible that there is example of Banach space which has that property.
This one.
The equality property.
The equality, yes.
Yes.
Oh.
This is open.
Oh.
One might say that this is the biggest open problem concerning Hilbert in Banach spaces. In Banach spaces, right? There are other problems. Yeah. So
Whether there exists exact ultra alpha homogeneous Banach space.
which is not the Hilbert.
Not-
Well, there is the second problem in these things is that there are very few examples. I will tell you very fast about that.
so
This is the list.
Is there a candidate or is this not known?
No. Well, you try to do this amalgamation, right? Kind of. There is some ideas in continuous model theory that they try to develop, but okay, no, I don't believe so for the moment. And this is the list. There is no more than that. There is the Hilbert space, there is the Gurari space, and there are these LPs.
So what goes wrong with Gurari space? I mean, it's Fresnel limits.
What is that?
What goes wrong with Gurari space? It's
Yeah.
Fresnel limits. You would expect that maybe, if anything, that it would work.
You mean why there is no equality?
Yeah.
Okay. Because, and this is very interesting that you were asking me this, because this is about global positioning. Isometries move nice properties of position to nice properties of position, like you might guess, right? One of them is differentiability.
Mhm.
So having a unique, since it is universal, you have peak points, you have these points in the sphere, and you cannot move this to another. This is impossible. So you cannot move one peak point because of this global versus, yes, these are these kind of things. You might ask what is going on with those. Yes? And again, the same. Isometries move full support to full support. Again, you might have a map who has norm 1, but without full support, with half, to another who has full support. And again, you cannot move exactly this one to this other one, right? So there are these kind of things which are exactly things we are trying to understand well. Yeah.
Seem to suggest that for 4 or 6, it's even worse. So
They are not approximate ultra homogeneous.
uh-huh.
And precisely because of that is why we started thinking about this omega categoricity and all these things. This is what I said at the beginning, these kind of things. That's because this funny 4, 6, 8, right? Because all of them look the same. The isometry, I will tell you, are exactly the same topologically, because there is this Banach-Lamperti, but they are not the same. I will tell you that in a moment, okay? Good. Well, remember I was telling you that you want to know not only that this being isometric is the same equivalent relation that being in the same position, but also topologically. Without entering into many details, because I'm not talking about that, you strengthen a little the property of extension. And you are not only extending isometries, but almost isometries. And this is what it says. I will tell you. Excuse me. This thing, right? So this is a delta embedding. Yes? The delta embedding is what I said here, this thing, which is almost an isometric embedding, right? And now, of course, you want to extend it to an isometry, but for sure, you cannot extend it exactly because one is a delta embedding. But you play, okay, but maybe with delta distance to a delta distance, yes, okay, maybe not to a delta distance, but something that depends on delta. And this is the case. And for Hilbert is 2 delta, for Gurari is 2 delta, and for the LPs is also, but I don't know the number exactly. I know that it exists, but I don't know the number. And this gives you extra information about these two relations, equivalence relation, having the same, being isometric or being in the same place, up to epsilon, right? That you move for every epsilon. I'm not going to talk about that because this is, and again, I'm going to insist, this is why we start thinking about this omega categoricity.
So I think you said, what's
Yeah.
a delta, can you say
Yes.
what a delta embedding is again?
Delta embedding is, so this thing here, we put it here,
Oh, okay, got you. Yeah, okay.
this thing here,
Yeah,
which
yeah.
means that the ball, which is like that,
I see.
doesn't move to, so this is the
Yeah,
bigger
I
one, something, right? Like
Yeah, I understand.
something
Well,
like
it
that.
should be convex.
Well, probably it is, more or less. So,
I guess it's straight lines.
well, now that there is the thing. Now there is this thing. What is this omega categorical, right? That I'm talking. This is the way we're talking. So there are many ways to say the same things. One of them is the most appropriate one. Which is this one. Because this is exactly placement, right? What is this double? This is the close orbits. This is the space, the quotient of close orbits, right? Right? Not the algebraic one. So you have what? E1 En, E1 Fn, if and only if. For every epsilon, there exists some t such that, well, now it depends what is the distance you choose in the product En. Doesn't matter, it is the same. Maximum of all of them is less than epsilon, right? You can move one to another up to epsilon. Yes? Okay, Heine-Borel is a fancy way to say that if I take a ball here, this is compact. This is exactly the same. Yes? In continuous model theory, they always use bounded metrics. That's a very important because otherwise we'll fall everything out. You can interpret what I said in the right way by saying these things, right? Simply that bounded things are good enough, are good. Okay, so not only so the talk is going to be about understand these objects here for a very particular spaces, which of course has to do with what I said before, right? And And okay, this is what it is interesting for us. This is the way to present omega categorical, but the way you can express it is as it is in there, right? And this is the unique separable Banach space with the so any other Banach space, separable Banach space with which is elementarily equivalent to this one has to be isometric. There is an isometry. Yes? Okay. And there is this thing well known, which maybe for some other people is interesting, maybe also for you, right? That it is exactly the same that to say that there is another Banach space, separable Banach space with the same ultra power isometrically, then it is because they are already isometric. That's a very strong thing. Okay, so this is what it says in here. I'm not going to insist because you already know that, and I am not going to use that. It is interesting, but not for what we are going to say. Okay, let's start with the first. So there will be two kind of examples, as I told you. S or K or S of X. This will be a Polish metric, I guess, has to be Polish, yes. Metric space. And then in the particular case of a Banach space, separable, yes. And this will be a very particular one that maybe you might guess, but I will not say now. It is there? No, good. And then there will be the similar thing for the LP spaces, yes? You might guess who I'm going to put in here. And now I will do exactly the same thing. Yes, I will tell you what does this mean, because this is not so common, although there is people doing things of this kind. So this you might guess, and this you might guess. Okay. We want to understand quotients, orbits of this kind in general. So it is a very good idea to know a little about isometries of E.
So do you want closed or did you just get one?
Yeah. Excuse me. I am so used to. Yeah. Very good idea if you know a little about how they look like, right? Or at least a part of them, a subgroup of them, because otherwise, kind of complicated, right? And that's why we went to this C of K for the, well, because for the C of K's, it is a classical result that any linear isometry is surjective linear isometry between C of K and C of K. It has a very simple, so what do you do? Move, there is a permutation in the category of the compact spaces, so an homeomorphism, you move, and then you put plus minus in a continuous way. This doesn't affect norm because the norm is the subnorm, right, of the absolute value. So putting 1 and minus 1 in a continuous way doesn't change value. Making a permutation in these colleagues doesn't make any change. And of course, the not so obvious way implication is to prove that all of them are of this way, right? That this is Banach stone. Of course, if you think for a while for this, well, yeah. It's more common is that, so why this plus minus? Because these are exactly the linear isometries of the real numbers, linear isometries, yes? Identity and minus identity. So when I change this to that, I am going to use isometries here, yes? Or linear isometries if it is a Banach space, yes? I will make several distinctions. Well, and this is what I said here, right? I want to replace this plus minus identity by some general closed-up group of the group of linear isometries of closed-up group of the group of isometries of some metric space S.
But
Yes.
S is just a metric space.
Yes.
How is this? A Banach space.
No, it is not a Banach space. It will be a metric space. So, because you will see that the argument is general enough that
Also,
Banach
it's a
space
Banach
doesn't make any difference, unlike for the LPs. And that's why I want to tell you this about the C of K of S. Because on the LP on S, this is not the case. There is a scaling there, which is a very different thing and makes the things more interesting and much more complex. Okay, so, well, yes, so this is what I said. There is this metric space, Polish metric space, very nice one, yes. And now you consider this new Polish metric space, which is C of 2 to, okay, so, well, I didn't want to, but it is there. So it is going to be 2 to the n, and you might wonder, but why not 0, 1? Unit interval. I will make a comment, very fast comment. So you could take C of K of S, right? Exactly the same way, and this is another space. Metric, Polish, anything very nice. But I put there 2 to the n because this will be the candidate I'm going to study. And I didn't put 0, 1, which is more natural, more used. Well, it depends. It depends for whom you talk. Obviously, maybe outside some places, 0, 1 is way more. But if you think for a moment, you want to know that these things say C of K, real values, right? Or the ball, yes. And now you want to know if this is compact, yes. And then there is this G is the isometry group. So the intuition will tell you that this to be compact, in particular, implies that G is big, meaning that there are many isometries. You have the possibility to move many things to the same place. So that because I recall you that in a Banach space, infinite dimensional Banach space, the unit ball is never compact, as it's very far away of being compact. So you have to collapse many points, and the only way is by having many isometries. If K is connected, for example, you are screwed in here. So with the signs, you can destroy just about anything. Not only because of that, right? But so you see, this is the main reason. Well, you can say many things, and you can study C of 2 of 0, 1, but not this. Yeah. Okay. On the other direction, why 2 to the n? Well, this will come later at the end, but 2 to the n. So following the same idea, you want to have many isometries, which means you want to have many homeomorphisms, many bijections in this category. But we do know this because this is the Stone space of the infinite countable atomless Boolean algebra, which is ultra homogeneous, which tells you, in particular, in a very precise way, that you have many automorphisms. Therefore, you will have many homeomorphisms, and of course, making arguments in the right way, you will prove and you will understand these things. Yes, this is the idea. Okay, so I told you we want to know what is that, and what it will come here are spaces of compact subsets. You already know what is that? Okay. I told you about this Banach stone. Well, Banach stone, if you change real numbers by S, maybe it's the same. It's true that all surjective isometries are of the same way. Maybe it's not. I have no idea in general for S's, for metric spaces. It is a little known what's going on with Banach spaces. So there are several of them for which it is true, the same thing, in the right way, which I suppose it is in there, yes? So there are several Banach spaces now changes by X, such that any linear isometry is of this form, where now V is going to be a continuous mapping from 2 to the n to the isometries, to the linear isometries of X, yes? But let us only work with those, because these are the ones you really understand well, and these are the ones that you can understand what is the corresponding quotient here, yeah? Exactly what it is. Okay, so, and the mapping is very simple in here. And I want to explain you this here, because when we will go to the LPs, you might have an intuition what it will be in there. What is the mapping? So you have to understand, you have to find an invariant on the orbits. If you analyze what are these, how these isometries, these Banach-Stone isometries look, they are permutations on the domain, continuous, bicontinuous permutations, right? And then plus minus. They do not change the image if you put the pi. The plus minus now it will be an isometry on S. And when you go to the quotient, you will go to the same place exactly. And when you compose F with an homeomorphism, the image is going to be the same. Yes? I am making myself or not very clear? No? No, I think not. So I have the pi, yes? So I have a mapping here, F, and I move it, how I call it, iota, right? So iota of F is what? Taking the image and then compose with the pi. If I take one of these isometries, which is determined by what? By some homeomorphism, and I'm mapping, picking in a continuous way, an isometry on G. I will write you down here, this thing. This is a continuous mapping from 2 to the n to the group G. Yes? And theta is an omeo of K, which is 2 to the n. So if I take this is exactly the same, yes? Iota of this is exactly the same as iota of F, because the image here is unchanged by that.
I'm sorry, I lost track. What is pi?
Yes, pi is the quotient mapping from,
Okay.
so you are identifying things who can be moved by G up to epsilon. So imagine that is identity and minus identity. So you are identifying X and minus X. Yes? So this is what I said. So you have this mapping here. And the first result here, interesting, non-trivial, is that this quotient is exactly via this iota bar, iota tilde. This is a surjective isometry. It's not just a bijection, it's not just homeomorphism, it is an isometry.
PSG.
Yeah, these are the isometries, Banach-Stone isometries, which are isometries of the form T.
Oh, okay. So just postulating it, because I was wondering how do you prove that everything is Banach?
No.
But you're not, okay.
Yes.
Ah,
Well, no, but I several examples where they are this way.
okay.
And in particular, if you find a subgroup such that the quotients are compact, the quotient by the full group is again compact. Yes? So unfortunately, you don't get the full explanation of what they look like, which is what we want. So, well, this is the thing. Well, you see, excuse me, I am not. So there is this little thing here because omega categoricity is about these things, right? There is an n here. These things. Yes? And then there is no. But this is simply because very simply I can put this thing here, right? So there is a little observation there that I'm passing, but this is the important thing, yes? Okay, and now, because of that, interpreting, since we are having this result, general result for a general G, if you put the linear isometries of X as a G, then you can have that, which is the first thing we wanted to understand. So in particular, this will come now. Well, these are the complete types in this model theoretical way, while these being isometric, they are the isometric types, the quantifier free types, yes?
But these are Galois types. I mean, you're talking about isometries, so they're not just.
Linear isometries.
Still, I mean, they are.
This is the structure where there is as a Banach space, this is a vector space, and then there is the norm.
Yes, I know that. But I mean, what you are defining here is a whole Galois type, because you can have two tuples that have the same type, but there is no isometry which sends one to the other. It's some sort of homogeneity.
But when there is this saturation, which is the case in here, it is the same.
But
Okay.
did you assume the intervals?
But they are. This 2 to the n is.
Okay.
But that's a very good point that I will write it down. Thank you. So, and now it comes one of the answers I wanted to know, right? The placement versus how do they look like? Okay. So if I apply the previous result to x equal real numbers, yes, I get the compact sets of Rn modulo identifying x with minus x. So these types, Galois types, they are the compact symmetric sets of Rn. But the isometric types, which is you have F1, Fn, and the isometric type is the norm defined by them, although it's not a norm but a semi-norm because they might not be linearly independent. Yes, it is general for F1, Fn. This is a semi-norm. I'm thinking a little, this is determined by a compact, symmetric, and convex set. So this is the distinction between the two of them. It is always the case that the isometric type space is a quotient of the complete type space. And the quotient map here is the convex whole. Exactly you see what is going on in there. Well, this is a picture, right? Which of course doesn't have anything to do. Okay, now why 2 to the n? I started that before about that. Telling you what's going on with 2 to the n. Well, you already know what is this infinite countable Boolean algebra. and this is ultra homogeneous. This is the Freisel limit of the finite Boolean algebras, which has the amalgamation, and therefore the limit, it is ultra homogeneous. And that's the key to prove what I said before, that all these quotients are isometric to the compact subset of blah, blah, blah. Yes? Of course, you need to work a little and make the details, but this is what is going on. Injectivity is more or less ultra homogeneity, and the isometric part, it needs a little argument, but it can be done. And then, of course, there is this other part. Why this is a surjection? And this is because 2 to the n is universal. You need to play a little, because there is this pi there, which is a kind of annoying, but finding the right selection, it will do the job. Yes? I mean that in order to know that any compact here is the subject, is a mapping in here, is the image, you simply know that any compact subset here is compact and metrizable, metric, therefore it is the continuous image of 2 to the n. Yes? There is this little thing annoying at the beginning, but also you can do it. Okay, and now it comes, now more or less, if you follow me a little, what I was doing with C of k, now you might have an idea of what I'm going to try to explain you in the LPs. Now there are no continuity. It's not topological thing, but it's measured theoretical thing. Yes? So the iota, this iota mapping now, there is a candidate that you might guess. So you have a F1 Fn in LP. What is this invariant you want to work with, which looks like the image of 2 to the n? Well, now is the distribution law. You might think, and this, because it is the case, that F1 Fn is a random vector. And you can consider the distribution. And the distribution plays the role, so this will be a probability on cubes, on 0, 1 to the n, or in other places, which will play the role of a compact subset. Yes? Of course, this is the idea, and there are several details which I'm going to try to explain to you. And well, 0, 1, yes, indeed. In previous versions, yes.
This
Excuse me.
this integral up here, what's little s zero? I mean, you're integrating, you know, this p power integral.
Where?
This is the distance. I'm just wondering how you're defining integral.
Yes, because this is
I mean,
a
you need to-
metric. Yeah, because otherwise, so you need. So this is moment. This is not in a Banach space. In Banach space, there is a very nice point, which is 0.
Yeah.
But if you don't have
Yeah,
that,
yeah.
and you want to have the same definition in general in a metric space, you need to put something like that.
Yeah.
And this S is arbitrary. S0 here is an arbitrary point.
You just
It doesn't matter what is the point by the triangle inequality.
I see.
You just put it in there. So, but you must put that.
Huh. Yeah, because otherwise you don't know what to integrate, right? There have to be some real numbers around.
So again, I was not really interested on these things, but I want you to tell you the exact difference between LP on S and NP on X, which is this scaling thing. Here there is no scaling because S is metric space. There is no summing vectors. There is no multiplication. There is nothing of this kind. So how to say, the nice isometries on these spaces are going to be those who are compositions, which I will say in a moment, of measure-preserving transformations, which are the right bijections now. Yes, if you follow me before with the homeomorphism. And then now, in a measurable way, you throw isometries of S.
Mhm.
Yes? Before there was a continuous way of doing that. Remember there was this plus minus one, plus minus identity, members of G. Okay? But if you are working with a Banach space and you are working with linear isometries, these are not the nicer ones. These are not only the nice ones. There is something that will come in a moment, which is called out star, which are these regular transformations, not measure preserving transformations, but regular transformations, which are those who preserve null sets. And they are the ones that they will show up. And this will create many more things and, of course, complications, yes? But more or less, it is the same strategy, yes? So, well, when S is X, which is a Banach space, this is what in Banach space theory is called a Wagner space. This thing here, exactly that, because you might take S0 equal to the origin, the zero. So you don't say anything, right? Because this is the norm, right? If you put the zero in there, you are doing that. And this is the norm in the Wagner space. Excuse me. This, because I'm thinking in real numbers. Okay, but if not, you have to do that. But I wanted to say something and it came out to my mind. Okay, it will come. Well, you have this space of finite p moments, probabilities with finite p moments, and there is and the finite p moment is this one, exactly what I did before. If you think that now mu is the measure image, this one, right? It is exactly what I said. There. Is F in. Okay, so and now there is a distance, which is somehow well known in some other context in math, which is this Wasserstein metric, which this is the way they present it, but I prefer that. This is the way I understand for what I'm doing, this very small thing. These are the probabilities on the product whose marginals you say in English? Marginals? Marginals, excuse me, are mu and mu. Yes? So you integrate the distance between these 2 points to the p against this pi who has some marginals, mu and nu. And this is exactly the same than that. In several cases, among them, the ones I'm going to use, this is a metrization, this is compatible with the weak topology, which is the one I am interested in, and which is compact in several cases. Among them, the ones I am interested in, yes? Okay, and now I come to this first, the definition of canonical isometries in this metric LP. Well, there are not so many options for an isometry to be called canonical, and these are the ones. Right bijections, plus putting plus minus one or isometries of G. I mean, plus minus one, I'm thinking in real numbers. Isometries of G in a measurable way. This is this thing here. Yes. And why you put that? Well, because these are the only ones that you can imagine that they are always isometries. And also because I knew, of course, that there is this Banach-Lamperti. Banach-Lamperti is still in Banach spaces for the LP or on. You have, okay, let me write you everything. Subjective, linear, isometry. This a ver, so let me see what is the order I put here. Where theta is not only, is not maybe measured preserving, but isn't regular. This will come after. And V in the isometries, in the linear isometries of real numbers, which are again. And of course, how this acts. Well, it depends how you do. We are doing this in the way that is appropriate for us. P of f applied to some number t is going to be what? F of theta of t, and then v of t in this way. You will find that some other times they put here this, because now the multiplication, if you multiply these two, then they will change this with this other. Okay, doesn't matter. This is what is appropriate for us. Well, in this way, if you put this representation, you take here the isometries with this SOT. The point was convergence. This is a Polish space. And this corresponds to the semi-direct group, the semi-direct product, excuse me, of out star with L0 by this representation. Yes? Again, I tell you, you can find this not with this order, but here with -1. The problem with -1 is when theta is not invertible, which will happen at some point, this doesn't work well. Okay? Of course, in here is a group. This is group, there is an inverse, but then I will not talk about that, but we did also some study of the Rolke compactifications. And in these Rolke compactifications, they show up embeddings, which are isometries, but not surjective isometries, and they are not invertible. Okay, so you need a representation which is also working for those objects. Okay, so now, okay, so what is the mapping iota in here? Iota was this that taking the image of 2 to the n. Now, law. The law of f, you put the pi again because you want to be not sensible to the isometries. There is the pi in there, so because of that, isometries in G. And now, working a little, also, you prove that this is a linear, this is not linear here, there is no linearity. It's a surjective isometry, yes? You have to work a little more than before. Yeah. And now, if you have a Polish metric space, which is omega categorical, then this LP is also omega categorical. Again, we were not interested on that. So in particular, if you think for a while, S metric space being omega categorical, it means in particular that S is bounded. Metric in S is bounded. But in a Banach space, I told you this is not the way the omega categoricity works. This is about the balls are omega categorical, say, yes? And because of that, you will immediately see that you need to consider more canonical isometries, those who are coming from this out star. Okay, and now it comes this nice group, not so well known, although it's old. Palmos already knew, and he has some remarks. Okay. So this is this out star. What is out star? These are all the transformations, Borel bijections. You might think they are Borel bijections so that lambda is absolutely continuous with respect to the image by gamma of lambda. Lambda is the Lebesgue in 0, 1, although you can define this in any other any other probability space. So lambda of A is equal to 0 if and only if. So in other way, gamma minus 1 to the Borel set of 0, 1 modulo null of lambda in Borel sets of 0, 1. I'm thinking in 0, 1, you can do it in general, yes? Null of this gamma star of lambda. This is an isomorphism. I am not saying that it's a measure preserving. This is different, yes? Okay, and now there is this number here, well, mapping, this is a mapping, this is not a number, which I will tell you what is that. So, so given some element of out star, gamma, you can define this surjective isometry, U, which we call it T of, or maybe phi of gamma, which is from, so let me put here 1, although it is general, there will be some T, but this is kind of not important. Well, it is easier if I put here 1 for you to understand what is going on. So this is going to be H gamma, and then it's going to be F of gamma. And this H gamma is what? Is the Radon-Nikodym derivative of lambda with respect to the gamma star lambda composed with gamma. And in other words, what does this mean? If you think for a while, you take the integral of gamma minus 1 of A against H of gamma. This is the Lebesgue measure of A. This is what it says. So this thing here is a surjective isometry. Linear surjective isometry. Okay? So again, I told you before, we are looking for isometries which are canonical or natural or easy to work with. So these are these other ones. And not only because of that, but because of Banach-Lamperti proved that isometries of LP are this way. All of them are this way. Yes? So you need to deal with them, and we could. Yeah? Okay, now there is this V now. I didn't say anything about V. And now you put plus minus 1 because it will not change the norm. If you remember, in the norm or the distance, there is an absolute value. If you are working in general in G, so you are composing with an isometry, so you will not change the D. Yes? So all of them will become again an isometry of the corresponding LP space. And this is what I said. The classical Banach-Lamperti theorem states, although Banach already, so this is a funny story, one of those funny stories. Banach already said that the isometries of LP are of this way, all of them, but no proof or no complete proof. Lamperti more or less proof. I believe also that there was some part there not 100% complete, but it is true. And this is the thing. In many cases, this is also true when you take LP with values in X. If you cannot split X into the LP sum of other infinite dimensional spaces, then this is also the case. and in many other cases. Okay. Now the problem, so now remember, we want to understand what are the quotients. We have a candidate which is this law, the distribution of the Fs. The problem with the distribution of the Fs in a Banach space is that since I can scale things, if you think for a while, by isometries I can make scalings, then I change the distribution. Because scaling is, so the distribution of some F, what is telling you? I take the image, I take an element there, I take a Borel set there, I take the pre-image by F, lambda, I take lambda of this, and this is the value. Yes? If I scale now the things, I change completely the role, right? One thing that looked like that in the image, now it will look like that. So I take the pre-image, this is completely another story. So I have to make this, I have to understand what's going on. And this is a normalization that we are going to do, right? I am not going to enter into the details, because this is what we call these spheres and measure spherical, this thing here, of this, that they come from some normalization, yes. In particular, for those measures of probability, the Wasserstein metric is compatible with the weak. And it is going to be very useful to understand what's going on with the quotients. Okay, so what's finally this invariant? So you have F, capital F, which is F1, Fn, and many mappings. And now you are going to normalize the sequence F1, Fn by sending them to a multiple of the constant mapping 1. Well, why you can do this? Because I told you at the beginning that LP is not ultra homogeneous. It's not even, and the argument I told you is take two mappings on the sphere, norm 1, one with full support and other without full support. You cannot move one to another by an isometry because isometry respect full support. Yes? But if they do have full support, then you can send one to the other by an isometry. So, and it is an if and only if. Yes? So there is the equivalent class of those who have full support. So how do you do this thing here? You take this F1, Fn. Now you define this modulus of F, which is a real value mapping, which is in there. This might or might not have full support, but I can put some epsilon value in the complement of the support. Now this has full support. I can send it to multiple of 1, right? Because both have full support. And now I have a sequence. I tend this sequence epsilon to the 0, and I do that. I prove that this is a Cauchy sequence in this compact space of the that I said called the weak topology, and there is a limit, and this is a distribution, this is a measure, and this is the definition. Of course, you have to prove all this. Yes, this is not immediate, but you can do it. And now this is the mapping now, which is way more complicated than before, which determines the full types, the complete types, these ones here. So the intuition is that for the C of K's is the image. For here is the distribution, but not any distribution, not the distribution of F1, Fn, but the normalized distribution, yes, in the appropriate way. And unfortunately, well, the work with the distances is much more complicated, and it is not an isometry, but it's not so bad. It's not ellipsis, but it's Helder with this number. Helder means, if you remember, is that it's kind of ellipsis, but with some alpha in here, right? Less or equal than, and here there is this alpha. In particular, because of this, when you restrict two balls to the ball of E, this is going to be a compact, in particular, if we come, okay, so in particular, again, we have many other examples of omega categorical structures, which is the thing it is in here, right? And there are many X's for which all isometries are Banach-Lamperti. So we have a description of the orbit spaces. They are measured, these spherical ones, and etc. Okay. Okay. So why 0, 1? Okay. So if you follow me, you say, okay, this is about 2 to the n. 2 to the n is a very nice, and you have this ultra homogeneity. And here I put 0, 1, but I said that 0, 1 it was bad for the C of 2 to for the continuous mapping. So what's going on here? Well, it turns out that it is the same, right? We were very tempted to put here 2 to the n as probability spaces. They are exactly the same spaces. 0, 1 with the Lebesgue and 2 to the n with the product. It is exactly the same space. So I could put here also 2 to the n, but it was like. And now, what is this ultra homogeneity we are using in our arguments? Well, it is this thing. You see? That's and here is countable. It's also true for countable partition. So what is telling you? That if you know the distance, the Lebesgue, so the Lebesgue measure, if you know, say for example, that the Lebesgue measure of omega j and omega prime j is the same. Yes, then there is a global bijection, so a measure preserving bijection who sends up to measure 0, sends omega j to omega j prime. Yes, this is this ultra homogeneity, but now of course you have to say that the probability is the same. And you can do it better as it is in there, yes? So it's a little more general. Well, this is what it says. It is written here. Okay, so and this is used to prove that certain that there is this Helder continuity in the two sides, etc. Right? All these things. And to prove surjectiveness, well, modulo this thing. It is the fact that the Lebesgue measure, the Lebesgue probability measure in 0, 1 is universal, right? If you give me a probability, a Polish space with a nice probability is going to be the image of the Lebesgue in 0, 1. Yes? Exactly the same like any compact is the continuous image of 2 to the n. Yes? And there is a selection. If you remember in the other case, there was also a selection in the quotient and all these things that unfortunately, or this is how it is, you need to deal with. So there is a selection of this kind about the quotient, right, that you need to, because now you need to approximate the distances too, and okay, but you can do it. And finally, really the way more complicated things is one of these inequality, this Helder inequality here. This was really something, but you could do it, which is about the continuity, yes? Okay, so finally, what's wrong? And this is going to be the very last part. What is wrong with these 4, 6, and 8, right? Because this sounds, I told you, maybe I didn't write it down there, but I told you that Banach-Lamperti shows that all isometries are of the form. There is an element of out star, and then there is a mapping in L0, so a measurable mapping that chooses plus minus 1. Yes? I didn't say P. P was not there. Well, because you don't need it. You only need it if you remember there was an H in there, H of gamma, and there was 1 over P. But groups are the same. the group is the semi-direct product of out star with else 0 with values in -1, 1. They are the same. The integral, if you take the norm, looks the same, except that the p is another number, yes? So what is different? What's going on with 4, 6, and 8? And so on and so on. Well, one little comment, the 2 is never considered in here because 2 is Hilbert. And of course, in Hilbert, this is another story. These are not only the isometries, they are always isometries, but there are much more, right? Because of Hilbert. This is another story. Yeah? Infinity also, because infinity is non-separable. But for the others are the same kind. Okay. But then why L4 is not approximately ultra homogeneous? Well, we know now complete types and isometric types. Now maybe if we find couples F1, F2, G1, G2, which have the same isometric type, but different complete type, meaning different spherical distributions, this will be a way, right? In a simple way. And of course, this is the case. Otherwise, I wouldn't explain you that. Well, this is what I said, right? For the other piece, yes, you can move, any partial isometry is up to epsilon, the restriction of a global surjective isometry, but not for this piece. Vale, so this is what I said, and I am here, right? Because all these things I told you. Okay, so here comes the very funny thing about the L4, L6, and L8, and so. Imagine that P is an even number, including the 2. So 2, 4, 6, 8, or whatever. You have many points, F1, Fn, in LP. Norm of the sum only depends on norms of the Fs, if they are independent and symmetric. So just knowing the value of the norm of F1, F2, Fn in L2, L4, L6 up to LP, I know exactly what is the norm of that. And this is because when you develop this thing, what did I say? K, right? You can develop this, and there are these numbers, these combinatorial numbers in there. There will be integrals of this form. They are independent. So this is the same that this thing here. You glue them together, and you will only see things of this form. Numbers, combinatorial numbers in here, and then things of this form. Well, which is that? Yes, this thing here. And this is very funny. Of course, if P is not 2K, but it's 3.1, what are you going to do? Well, you need to take this Taylor, and good luck. Well, good luck, no, because you cannot do it. So, so if you think for a while that you have such a sequences, the isometric type of Fj's and Gj's is going to be the same exactly when this holds here. Because if I multiply Fj by Aj, these coefficients, they are again A1, F1, An, Fn, they are again independent and symmetric, yes? So you can apply that. So for L4, L6, L8, being isometric is very simple. That's what is going on. Okay, so now with my student, Victor, we were thinking, so, but then we must have a very simple example with two. And this is the case. And it turns out, well, here there are the details. Since I'm going to leave this here, if you are interested, you can take a look. But there, it is a very simple example, which is, this is one mapping. So I am going to take 1 and minus 1 in the 0, 1 half, 1, 1 half, 1, minus 1. This is the first, this is symmetric. And here, of course, here this is symmetric too, but this is not independent on the very first one, because if the first one was that, what I need to do is to copy this thing in here and copy the same thing in here, right? And in this way, easily you see that you are making the first one and the second one, which is a modification of this one, being independent. This is how you do it. And the same for this one. So very simple one. Making a very simple simple computations, you get this value, and this is what I said. You take these examples, you put it in the first, in these two intervals, exact intervals, and both are independent of this one, but this and this and this and this has a very different distribution because they are normalized already, but the values are not the same. And remember, the distribution is the Lebesgue. Push the Lebesgue to the image. If the image is different, no way it's going to be the same distribution, right? And this is what's going on. In a very simple way, you find why they are not approximate ultra homogeneous after doing all the work. Let me see. Well, this is the control example, S and this copy F, and S and copy G here. Well, and this is some, well, isometric subspaces because, well, you compute the 2 norm and the 4 norm of these ones, and they are exactly the same for S, obviously, and for F and G. And they have different distributions because they have very much different, because they are normalized, I already said, and they have very different values. Yes. Well, before I make this very last thing, I wanted to say a couple of things about this L4, L6, and L8. Okay, so finite dimensional subspaces of capital L4, L6, and L8 are subspaces of little L4, L6, L8. This is a very strong thing because if you think for a while, this L4, L6, little L4, L6, they are like the discrete version of the capital L4. So they have discrete distributions. This is not the case at all in the other L4s, in the other LPs, excuse me. So this is really, this was already known a long time ago, but they were not thinking on those things, right? I wanted to say something else, but I'm running out of energy. And, please let me go back and see. There was something I wanted to say. Well, yes, we have, of course, the same other examples for any other LP, P even, the same kind. You find a very simple way, some algorithm to choose these Fs, not two, more than two, depending on the dimension. And it depends on the P, right? And it has to depend on the P because some other things. And then, yes. This is what I wanted to say. Before, when I had to explain why L4 is not approximate ultra homogeneous, I was always using the following. Isometries, global isometries, move nice properties to nice properties. I already told you I'm going to insist. In the case of C of K's, the C of 0, 1, C of 2 to the n, if you have a point of the Gurari, if you have a point which is where there is one norm, only one, which is smooth, it will go to a smooth point. In the case of the LPs, if it has full support, it will go to full support. Yes? In the case of a finite dimensional space on the LPs, which is complemented, nicely complemented, this means what? That there is a projection of norm, a small norm. If you move this subspace, which is nicely complemented, there is a linear projection. In a Banach space, not always there is such a thing. Nice, so with a small norm, not depending on the dimension. So if you take a global isometry, a Sagittarius isometry, and you move this to another, to the image, this is also, and it's very simple algebraic thing, is nicely complemented. Yes? So if I give you two subspaces, isometric ones, but this is positioned in a way which is nicely complemented, and this other copy is positioned in some other way, in some other place, which is not nicely complemented, then I can show you, I already showed you that I cannot move this to this other by an isometry. And this exists. But the example to do that is way more complicated than that, right? This is some sequence, infinite sequence, and then you take the finite thing with random variables, independent, kind of this thing with way more complicated. Yes, so, and I think this is all. So I put a list here of certain papers which might be interesting for understanding that. So this is the paper that we are finishing. It's almost done. There was something about this Royke compactification, which is already done. And we will put it soon in archive. And thank you.